Well, we're doing a pair of tapes, a pair of messages, the fourth of a series of pairs, on cosmic codes, hidden messages from the edge of eternity. And this final pair of messages we're calling metacodes. We've talked about microcodes, macrocodes. These are metacodes, beyond the codes, if you will. And the first of these will be on a digital universe. We had our first session was on an introduction where we talked about the nature of cryptography. Many people writing in this area have no cryptographic background, which caused us to jump into this. And after some general background on extraterrestrial messages and languages and those kinds of things, surprising scientific studies that have been behind that, we then got into microcodes. The second pair was on microcodes, yots and tittles, these interesting aspects of the Hebrew language that we discover are there to carry several levels of meaning. Many people say, well, the Hebrew lends itself to wordplay. Indeed, it does. It never occurs to them that the Hebrew language may have been designed for that very, very purpose. So, in any case, our third session was on macrocodes, these codes that are anticipatory, these codes that are from outside time. We went through a series of messages on that. And this fourth session is on metacodes, those codes that are beyond our horizon, beyond the Scripture itself. It's in a denotative sense. And it's going to be in two parts. The first one, we'll talk about our universe, but with the specific twist that it's digital. What do we really mean by that? A very shocking discovery. The whole nature of reality has been really altered by recent discoveries and insights. And then we'll follow that opportunity to explore the DNA, the code of life itself. Let's just start with a little bit of background, familiar to those of you that are familiar with some of our briefing packs. There are four basic forces in the universe. The first is, of course, gravity, electromagnetic force, the strong nuclear force, and a weak nuclear force. So there's gravity, electromagnetic, and then two kinds of nuclear forces. Now, gravity, most of us are familiar with. That's what causes an apple to fall to the ground. That's what keeps our feet on the floor. It also binds together our solar system. Gravity operates in very, very long distances. It keeps the Earth and the planets in their orbits and prevents the stars from exploding. Those are all from the force of gravity. And, of course, even goes beyond that and guides the galaxies in their motion. So the gravity is perhaps, in some respects, the most mysterious of all the forces. Another force that is the force that holds the atoms together, electromagnetic force, determines the structure of the orbits of the electrons in the atoms. And because of that, it governs the laws of chemistry. Its forms that this force takes place is X-rays, radio waves, light, all different kinds of forms. And it can overcome gravity on the Earth. So gravity goes on great distances. Electromagnetic can overrule it in the shorter distances. It can dominate other forces down to the size of the nucleus of an atom. Intriguing that the gravity is cosmic, electromagnetic in the intermediate sense. Then when we get to the atomic level, we discover there's two nuclear forces. One they just call the strong nuclear force. And this is the force that binds together the protons, the neutrons, and the nucleus of the atom. And that may sound strange, but you realize that we've all learned that positive charges repel. And yet you have the nucleus composed of positive and neutral charges. What holds them together? Well, a very unusual force called the strong nuclear force. It's the balance between the strong force and the electromagnetic forces that limit a nucleus to about 100 protons. They will go from 1 to approximately 100 because of the interaction of those two forces. And that the energy released from the strong nuclear force is substantially greater than the electromagnetic force. The electromagnetic force is actually the force that's released in a chemical explosion. When you have a chemical explosion, the forces that are causing that are really, strangely enough, the electromagnetic forces. The strong nuclear force is obviously vastly more powerful than electromagnetic. The strong nuclear force is what really causes stars to shine. Each of these forces, of course, are essential for life. That leaves us the last one, the weak nuclear force, which really governs atomic instability and radioactivity. It results in the disintegration of the heavier nuclei, and it can create heat, as in the decay of radioactive elements in the Earth's core or in a nuclear power plant. Now, what's interesting, having gotten this just a review of these four basic forces, there is an observation that even secular scientists admit to, and that is the apparent presence of deliberate design in the universe. Even Paul Davies, a secular writer, scientific writer, says it seems as though somebody has fine-tuned nature's number to make the universe. The impression of design is overwhelming. And they even call this apparent design in the universe the anthropic principle. What they mean by that, it seems as if, as you study the universe, that it's been designed specifically for man. And that's not a preacher talking. Those are observations of secular scientists. So they call it the anthropic principle. Where this comes to vivid awareness is when scientists attempt to build a model of what we know about the universe. And as they build a mathematical model of what we know about the universe, they discover something very strange. Is that almost any ratio or relationship of the numbers, if you alter it, even in a model, just a little bit, it falls apart. Let me give you an example of that. There's a coupling constant, the gravitational coupling constant. If it was a little stronger, all stars more massive than our sun, by a factor of about 1.5 times, they would burn too rapidly and inconstantly to maintain life-supporting conditions on planets nearby. If this coupling constant was a little weaker, all stars would have less than 0.8 times the mass of the sun, and there would be no heavy elements in our universe. Another coupling constant is the electromagnetic coupling constant. If it's weaker, molecules for life would cease to exist. And if it was stronger, molecules again would cease to exist for a different set of reasons. Then there's a strong force coupling constant. If it was weaker, multi-proton nuclei would not hold together. Hydrogen would be the only element in the universe. If it was slightly stronger, nuclear particles would tend to bond together more frequently and firmly. Hydrogen would be rare in the universe, and the supply of various life-essential elements, heavier than iron, would be insufficient. In other words, these relationships determine the periodic table, which gives us the richness of the elements that we take so for granted. The weak force coupling constant, if it was larger, there'd be no such thing as helium or any heavy elements. If it was weaker, everything would be helium. These mathematical relations are very delicate. And I won't get into some of these, they're very technical, but if the electron to proton mass ratio was different, if it was larger, molecules would not form and life would be impossible. If it was smaller, molecules again would not form and life would be impossible for different reasons. Now, these atomic physics factors I'll just step through primarily because most of us are probably not close enough to particle physics or atomic physics to relate to some of these. But let's take something we can all talk about. Let's think about the sun. Sun and the Earth. The mass of the sun, the color of the sun, the distance from the Earth, the age, the distance from the center of the galaxy. If any one of these were changed, life would be impossible. Let me take surface gravity as an example. If our surface gravity here on the Earth was stronger, our atmosphere would have too much ammonia and methane. It would not support life. If it was weaker, the atmosphere would lose too much water. The Earth's crust. If it was thicker, there'd be too much oxygen would be transferred from the atmosphere to the crust. And if it was thinner, volcanic and tectonic activity would be too great. See, the point is these things are in balance. If the rotational period, if our days were longer, more than 24 hours, the diurnal temperature differences would be much greater, too great to really support life as we know it. If they were shorter, there would be wind velocity problems. Actual tilt. If the tilt was greater or lesser, surface temperatures would be great. And that's not obvious until you model it. The albedo of the Earth, the reflectivity of light from the Earth. If it was greater, there would be a runaway ice age develop. And if it was less, a runaway greenhouse effect. There's a balance between the ice age and greenhouse that happens to be just balanced where we are. The Earth's magnetic field. If it was stronger, the electromagnetic storms would be too severe. In fact, we're going to have some very marginal conditions occur in the year 2000 because of the sunspot cycle, and the power people are worried about that. And if the Earth's magnetic field was weaker, we'd have inadequate protection from the hard stellar radiation. So literally there are hundreds of these kinds of factors. The CO2 and water vapor levels. If it was greater, the greenhouse effect was less, there'd be an insufficient greenhouse effect. Here's one that I enjoy is the ozone level. It's interesting, you've probably heard a lot about this. If the ozone level was greater, our surface temperature would be too low. If it was less, our surface temperature would be too high. And it'd also be too much UV radiation at the surface. Now, this comes up because the ecologists love to tell us that, the ozone layer, if it changes 0.1% of 1%, it's going to bring cosmic doom on the planet Earth. Well, without getting into those arguments, it's interesting. If the ozone layer is that delicately balanced, who balanced it? See, the very argument that it's in jeopardy is the same argument that it was designed carefully. If that ratio is so critical, that's an argument against it happening by chance. Many people don't stop to think that through. Now, this is just the anthropic principle. Now, one of the things that most scientists take for granted, there's a giant controversy brewing about the speed of light. In the 17th century, Johannes Kepler, René Descartes, most of the scientists in the 17th century believed that light was instantaneous, or putting it another way, that the speed of light, which is typically mathematically designated as c mathematically typically refers to the speed of light, that c was infinite, that the speed of light was infinite, or put another way, that the speed of light is instantaneous. That was just the presumption, and when René Descartes took that view, then everybody did, because he was the thought leader of that era. And it's interesting that in 1677, a Danish astronomer by the name of Olaf Romer very carefully measured the elapsed time between the eclipses of Jupiter and its moons. And it did it when it was at one end of the orbit and then again at the other end of the orbit, and they knew the distance, and by measuring that carefully, it was an interesting way to measure the speed of light. And he measured the speed of light, determined that it was finite. His measurements, he concluded from his measurements that the speed of light was about 300,000 meters per second. Now what's interesting is, this was in 1677. For 50 years, scientists refused to accept his results. They just knew that speed of light was infinite, and his character with his experiment, they just didn't hear it, they didn't want to, they just didn't believe it. Until an Englishman by the name of James Bradley, virtually 52 years later, repeated the experiments and confirmed Romer's results, that the speed of light was not infinite, it was finite. You say, well, gee, what has this got to do with anything? Well, it turns out that the speed of light has been, over the last 300 years, has been measured at least 163 times by 16 different methods. And today, almost any competent physicist will tell you that the speed of light is fixed. It's a constant in the universe. There are, though, a few people that are beginning to challenge that view. Barry Setterfield in Australia and Trevor Norman, a mathematician, published some time ago a study where they captured the raw data from all these experiments over the centuries and analyzed on a computer and discovered some strange things. The Romer data from 1677, that's from the eclipse of Io, the moon of Jupiter, their measurement of the speed of light was about 307,600 kilometers per second, give or take 5,000, okay? In 1875, they measured the speed of light at Harvard using essentially the same method, the eclipses of Io, and their conclusion was 299,921 plus or minus 13. Now, obviously, in the 2 centuries that transpired, our technology and instrumentation became more precise, so their error range is much smaller. Instead of 5,000 kilometers per second, it's down to 13 is their estimate, plus or minus 13. In 1983, at the National Bureau of Standards, using a different technique altogether with lasers, they've determined the speed of light as 299,792.4586 plus or minus 0.00003 kilometers per second. In other words, in modern terms, they've measured the speed of light much more precisely. You notice the error band is a lot smaller, obviously, as the centuries went by. But I want you to notice something else that's rather strange here. Romer's data implies 307,600 plus or minus 5,000. That is still, as a mean and as a range, substantially faster than the Harvard data 2 centuries later. Harvard measured it more accurately, but it doesn't, in other words, if Romer's error rates are accurate, the implication is that Romer's data implies a higher speed of light. And to make a long story short, this is just a very clumsy summary of Setterfield's work, but taking literally over 100 of these experiments and analyzing them on a computer, Setterfield and Norman published the view that the speed of light has been slowing down through the centuries. It's almost asymptotic now, meaning it's now slowing down very, very little, but in the past it apparently was slowing down a great deal more. And Alan Montgomery, a mathematician in Canada, has confirmed their results and analyzed on a computer. In fact, has a 99.9% correlation to a cosecant squared curve. In other words, going back in time, if they're correct, going back in time, the speed of light was much, much faster. Most physicists have a whole list of reasons for not accepting that view, but gradually and I want you to remember, when Romer published his data originally, it took 50 years for science to accept the results. And I'm amused by that because I see it's taken at least 10, 15 years for people even to take Setterfield seriously, although lately they're taking him more and more seriously. Now, I won't get into the properties of space. Space itself has physics properties: permittivity, permeability, zero-point energy, and the intrinsic impedance. If any one of these are isotropic, subject to isotropic changes, that would affect both the speed of light and also the nature of atomic behavior. That's going to impact some other things. Now, one thing, I didn't get a slide put together for it, but there's an astronomer by the name of William Tift in Arizona. Well, before I get to that, most of you may realize that in the 20s, they discovered that the stars are shifted to the red. The spectrum of the stars is shifted to the red. They call that the red shift. And Edwin Hubble postulated that that's because these stars are moving away from us, like a Doppler effect. So the Hubble's law suggests that the further they are, the more they're shifted to the red, the further away they are. We have a universe that appears to be expanding. And the concept of an expanding universe has been a foundational view of science for many decades. And that leads to a lot of other inferences and conjectures and conclusions. Well, William A. Tift is an astronomer in Arizona. There's also Abt in Germany. Both have been collecting information on the red shifts very precisely. And he was first attracted to this because he noticed some of the stars are not shifted to the red, they're shifted to the blue, which implies they're coming at us. But more importantly, he's discovered, strangely, that the amount of the red shift is quantized, meaning the amount of red shift you measure on any star is always a multiple of a specific number, which means it's quantized. Well, the implications of that are that implies that it's not an analog process, it's a digital process. It turns out, for reasons that are not obvious on the face of it, that the quantization of the red shift discovered after 20 years by William Tift is a strange possible corroboration of Satterfield's data, because if the speed of light's been slowing down, it would cause that quantization in steps because of the atomic behavior. There are some very advanced papers being submitted for publication as we speak, and we'll see how that suffers the gauntlet of peer review. But the point I'm getting at is that we're discovering, as we look at our universe, many of the beliefs that we've had in the past are being challenged by data. One of the interesting areas is this area of hyperspaces. Most of us take for granted we live in three dimensions, length, width, and height. And then those of us that have a little bit more thinking or reading about it also realize there's a fourth dimension called time. Length, width, height, three spatial dimensions plus time. Well, it's interesting that Nachmanides, who was a Hebrew scribe in the 800 years ago, the 12th century, he and Maimonides, both of them were at the peak of the so-called Geonic area or the Talmudic area in Hebrew writing. Both of them recognize that from Genesis chapter 1, that the Bible portrays the creation of the universe is that matter, energy, time, and space all had a beginning. And that's a very sophisticated view. Most people even that don't realize that not only did matter and energy have a beginning, but space itself did. They're interrelated. But they recognize that from their studies of Genesis 1. But Nachmanides noted in his commentary on Genesis 1, note something else. He felt from studying Genesis 1 that the universe had 10 dimensions. Only 4 of them are knowable, 6 of them are not knowable, as in his vocabulary. Well, it's interesting that today, among the particle physicists, they have determined that we live in a universe of at least 10 dimensions. Some say even maybe more. Only 4 of these are directly measurable, length, width, height, 3 linear lengths, plus time. 6 of them are curled in less than 10 to the minus 33 centimeters, and therefore they're not directly measurable, they're only inferable by indirect means. We speak of hyperspace as spaces of more than 3 dimensions. The 3 dimensions you and I know, the length, width, height, we're comfortable with because we experience it directly. Time's a little more elusive. It's a linear dimension that we sort of take for granted. There is a discovery that is very disturbing we're going to get to. I think I'll just deal with it right now. You and I would think that if we take a piece of length, say something that's 3 feet long, we can cut that in half, right? And whatever we end up with, we can cut that in half, right? So we start with 3 feet, we've got 1.5 feet, we can cut that in half, we have, 3/4 of a foot. And as we keep cutting this, it gets smaller and smaller and smaller. Every time we cut it in half, we have half as much, right? We would assume, at least conceptually, that we can always, whatever's left, cut it in half. If it gets down to 1 inch, we can cut that and get 1/2 inch. You cut the 1/2 inch, you get 1/4 inch, and that can go on forever. We recognize it finally gets so small that we can't manage it, but in our mind's eye, we always assume that we can always cut it in half. Again, it turns out to be a very disturbing discovery. that if that gets down to 10 to the minus 33 centimeters, below that it has no existence, that you can't cut it in half. There are particles, subatomic particles, electrons, photons, so forth, all these different subatomic particles. They discover that smaller than a certain size, they cease to have locality. They don't cease to exist, they cease to have locality. I'll come back to that. Now, that's true of length. It's also true of mass. You keep cutting mass down. There's a point at which there's a thing called Planck's constant. When you get down to certain levels, it doesn't exist smaller than that. You can't cut it smaller than that. It doesn't exist. It's digital, is the point. Time is an example. Figure you take an hour, cut it in half, that's 30 minutes, cut 30 minutes down, you got 50 minutes. Same thing, get down to a second, a fraction of a second. When you get down to 10 to the minus 43 seconds, it doesn't exist smaller than that. Now that turns out to have very, very disturbing implications, and that's what we're going to get into here in a minute. But before we get into that, there's another piece of background I want to lay down, and that has to do with a hologram. Most of us have seen holograms. Many of the things we've seen aren't really holograms. They're synthetic things for advertising stuff. Let's assume I'm wearing a necktie. And let's assume I hold up a Bible in front of my necktie, and you take a picture of that. Could you tell what kind of a necktie I'm wearing? You couldn't, because my Bible would be, or whatever, would be blocking that, right? A picture, a photograph, as we're familiar with it, is a space-time representation, spatial representation. It's two-dimensional, and you have what you've got. If you were to make a hologram, that's a way of making, in effect, a photograph without lenses. The way you go about that is you arrange a laser. A laser generates very coherent, controlled light. You arrange a laser with beam splitters so that it illuminates the film. There are no lenses. The film, you put a piece of film, and let's assume I'm here, we're wearing a tie with my Bible again. You arrange it so the laser light can fall on me and on the film at the same time. What the film records is the interference of the light that comes direct, the light that's reflected. When you take that film, after exposing it, and put it through a darkroom procedure to develop the film, you hold it up to natural light, it looks like a cloudy piece of film. It looks like a darkroom mistake. You can't see anything. But if you take that film then, having been developed, and illuminate it with the laser that created the first place, that piece of film begins to look like a window into a three-dimensional space. When you look through that film, you can see me. At first, it looks like a photograph, except you notice something interesting. You can move your eye, and if I was holding this, say, a Bible in front of a necktie, you could move your eye around and see what kind of, you could look behind the Bible and see my tie. Follow me? It's a three-dimension. That's why when they were first, I was with Emmett Leith and University of Michigan when they first discovered these in 1963. They have very, very strange properties. Now, it's going to be useful for us to understand a little bit of what these properties are. What the hologram records is not the space-time image. It records the frequency information. Every piece of information about me on that film is distributed over the whole film. So when you look at it that way, you just see the blur. It looks like a cloudy piece of film. It's when the laser hits it that it gets reorganized the way it was in the first place that you can see a three-dimensional image. Well, this means that the hologram has some peculiar properties. For example, if I have a photograph and I cut it in half, you have half a photograph. If I take a hologram and cut it in half and give it to two of you, you both end up having the complete picture. Because you take your half the hologram and illuminate it with a laser, and you have a complete picture of me. If I cut a hole in the hologram, you can always look around the hole, and you always have, it won't be quite as sharp. You lose a little resolution. But the point is every piece of information is distributed everywhere over the hologram. So the hologram acts as a window in three-dimensional space. A mathematician would point out that the hologram is a Fourier transform of the image. One of the things that's interesting in our book Cosmic Codes that we deal with is the discovery that the Bible, first of all, has integrity of design. You've got 66 books that were penned by 40 different guys over thousands of years, and yet you discover it bears evidence of design. Same themes, integration, use of language, All kinds. That's what our whole book tries to unravel, all that. But there's something else we discover, and that is that it's been designed, not only has it been designed, it's been designed in anticipation of hostile jamming. If you're a communications engineer and you're trying to create a communication system between point A and point B, and you're anticipating hostile jamming, there's several things you can do. One of the things you do is you spread your message over the available bandwidth. You don't concentrate it. Just one of the techniques. It's interesting that as you study the Bible, you discover that's also been done of the Bible. It's been designed to avoid any effects of hostile jamming. Let me give you some examples. Where's the chapter in the Bible on baptism? Where's the chapter in the Bible on any topic? It isn't. Any important topic is spread throughout the whole Scripture. You can take a Bible and tear a page out. You may lose some resolution, but you don't lose any key doctrine. And that's exactly what God announces in the book of Isaiah. I've established my line precept upon precept, line upon line, here a little, there a little. It's been distributed. One of the ultimate ways that you can distribute a message visually is to do it on a hologram. Because that hologram gets damaged or torn or something. Doesn't matter. You still will end up, if you got part of it, you've got the message. It's interesting, we take a hologram and you look at it in natural light, it has no form or comeliness that you would desire it. Looks like a darker mistake. But when you illuminate it with the light that created it in the first place, you get an image. It's interesting, the Bible is the same way. If you examine the Bible in natural light, it looks like a collection of quaint legends, histories, what have you. It has no cohesion. But when you illuminate the Bible with the light that created it in the first place, in the name of the Holy Spirit, what do you get? You get an image. Of whom? Of Jesus Christ. The exciting thing about the book of Genesis is not, to me, the creation, that stuff. The exciting thing about the book of Genesis is Jesus Christ is on every page, if you know how to look. Again, we have these Fourier transform properties. There's also, we could go through, and I didn't want to bore you to death with a lecture on this, but there are about 4 main mathematical equations that are analogous to the attributes of God. There are 4 equations that have to do with the nature of light, and each one of those is exactly parallel to the nature of God. Example of this is the idea, perfectly collimated light is light that mathematically sits at infinity. It's perfectly parallel, perfectly collimated. Well, it's interesting, in James 1:17, it says, every good gift and every perfect gift is from above and cometh down from the Father of lights, with whom is no variableness, is what your King James says. The actual word is parallax, neither shadow of turning. And that's just one example, there are others. This whole idea of the Bible as a hologram, and that it's transcendent of parallax, I mentioned already this idea of spread spectrum design. One of the most sophisticated techniques in advanced communication engineering is this idea of spreading your message across the spectrum, exploiting the entire bandwidth to get an immunity of jamming. And we discover the Bible embodies those techniques, interestingly enough. And that's exactly what is declared by Isaiah in 28:10, for precept upon precept, line upon line upon line, here a little, there a little, and so forth. Anyway, I really want to get into a little more about our digital universe. I don't want to make this a physics lecture per se. The interesting discoveries they're making absolutely shatter most of our traditional concepts of the nature of our universe, the nature of reality. It's interesting, I couldn't resist the quotation by Sir Isaac Newton. Many people, of course, know him as one of the greatest scientists that have ever lived. What most people don't know is that he wrote over 1 million words. He wrote more about commentaries on Daniel Revelation than he did on physics, by the way. Kind of interesting. But anyway, one of the quotes, he says, the entire universe is a cryptogram set by the Almighty. Boy, if he only knew, because as we get into quantum physics, particle physics, they're discovering some very disturbing things. Now, we, of course, we've been subject to this view, classical view of science. The scientists have recognized the universe had a beginning. They know it's a finite universe. So it has not been here forever. There's a lot of evidence that it has, and I won't go through the whole thing on that. But that's given rise to a family of models called the Big Bang models. So scientists will agree, for lots of reasons, the universe hasn't been here forever. It had a beginning. The other thing many people may not realize, it also has an end. We know from the laws of thermodynamics that it's in wind down. The whole universe is subject to what they call the entropy laws. first and second laws of thermodynamics, it's winding down, which means sometime, it's billions of years, whenever, but it's eventually going to wind down. And its ultimate wind down is called typically by mathematicians or astrophysicists or the ultimate heat death. Every time something happens in the universe, something gets done, it takes energy, some of that energy is lost. None of these processes are 100% efficient. The loss creates an ambient increase in temperature. It takes a difference in temperature to accomplish work. The day will come, at least in theory, someday when the universe is of uniform temperature, no work can be done. That's what they mean by, that's why they call it the heat death. This is why we know that we live as mankind between two boundaries, a beginning and an ultimate heat death. The great discovery of 20th century science is the realization that our universe is not infinite, it's finite, has staggering implications. The laws of thermodynamics, most of us probably know the first law of thermodynamics, the conservation of matter and energy. You can convert matter to energy, but you can't destroy it. You can't create it or destroy it. Some people summarize that. You can't win. Okay? Now, the second law of thermodynamics is the bondage of decay, or the entropy laws. And what that really says is you can't even break even. In other words, every time you convert matter to energy or energy from one form to another, there's always a loss. The efficiency is never 100%, it's something less. That shortfall from 100% contributes to is in effect a heat loss. It's interesting how both of these fundamental laws in science are explicit in the Scripture. The whole idea of conservation of matter and energy is implicit in a number of passages where God ended his work. In other words, the universe is wound up and that's it. The works were finished from the foundation of the world, Hebrews tells us, 4:34. All things that are, and then you preserve them all. Okay. The bondage of decay, the second law of thermodynamics, is also in the Scripture in some surprising ways. Psalm 103 speaks of the universe, says, they shall perish, grow old as a garment, speaking of the heavens and so forth. Isaiah 51:6 says, the earth will grow old like a garment. See, this perception that the universe is in wind down is all through the Scripture. Heaven and earth will pass away. They're going to be replaced, obviously. This idea of thermal decay is something that's pretty obvious to anyone that's had any physics. Heat always flows from hot bodies to cold bodies. If the universe was infinitely old, the temperature throughout the universe would be uniform. Heat's always flowing from hot to cold. So as time goes on, it moves towards uniformity. So in other words, since it isn't uniform, it isn't infinitely old. The universe had a beginning and was probably just as significant as destined for an ending. Now, I'd like to pause here and talk a little bit about Frank J. Tipler. Frank Tipler is the professor of mathematical sciences at Tulane University. He happens to be an expert in astrophysics, information sciences, particle physics, a few other areas. A lot of very deep thinkers have been focusing on the Big Bang models, trying to wrestle with some of its problems. There are other scientists that probe this whole idea of trying to understand this ultimate heat death. What Tipler decided to do was to try to put together in one model what we think we know about both of these. So it's a very, very ambitious project, but he undertook it. And as he undertook this project, he made two discoveries that shocked him. Here's an atheistic scientist who undertook this activity, and he came to two conclusions. His first conclusion he came to as he wrestled, dealing just with the laws of mathematics and physics. He came to the conclusion that God exists. God after the Judeo-Christian tradition. You say, of course, well, no kidding, Dick Tracy, big deal. Don't ever underestimate profundity when a PhD can come to know God. That's exciting. But the second conclusion he came to surprised him even more. He came to the conclusion, just using the laws of physics and mathematics as we understand them today, that all life is destined for a resurrection. And we're going to talk a little bit about that in the next session. But he published a book called The Physics of Immortality, in which he concludes that not only is the universe finite, but that all life within this universe is destined for a resurrection, strictly from the laws of math and physics. So, I don't recommend his book particularly unless you have an appetite for differential equations. You can learn more about the subject by reading the most important chapter in the Bible. What's the most important chapter in the Bible? Well, Paul would suggest 1 Corinthians 15. We all know 1 Corinthians 13, the love chapter. His argument in 1 Corinthians 15 is that if we don't have the resurrection, we have zero. And the resurrection chapter is absolutely a stunning chapter to study. We've discussed in a number of our briefings, particularly our briefing pack called Beyond Perception, that mass, length, energy, and time are made up of indivisible units called quanta. There's units below which you cannot divide them. That's a very disturbing discovery. In 1906, J.J. Thomson, brilliant scientist, got the Nobel Prize for proving that electrons were particles. That doesn't surprise us today. That was back in 1906. It's kind of interesting. In 1937, his son got the Nobel Prize for proving that electrons were waves. And this really highlights a basic paradox in physics, because these subatomic things, whether you're talking electrons or photons, any of these quanta, can behave like particles. There's certain attributes of a particle. They also can behave like waves. They've discovered that an electron, if you're shooting an electron down a path where there are two slits, it goes through both of them simultaneously. It bears mathematical evidence of that. And that makes no sense. Now, if you thought that made sense, you weren't listening carefully. Now, the other disturbing thing is there's compelling evidence that the only time that these quanta manifest themselves as particles is when they're being observed. And that makes no sense either. And they're not joking. This really, really troubled Einstein and Niels Bohr and some of the great thinkers at that time. Niels Bohr is one of the great scientists in particle physics. But he made a great quote. He says, anyone who isn't shocked by quantum physics has not understood it. It makes no sense the more you get into it. And one of his conclusions from what they think they know about particle physics is that the behavior of particles, they behave in such a way as to imply they're all immediately connected. In other words, every electron in the universe seems to know what every other electron in the universe is doing. That makes no sense, I know, but that's what caused one of the great physicists to commit suicide because he couldn't handle it. Now, Albert Einstein really launched some of his early papers in 1905, started the whole quantum physics thing, but he became very disturbed at the way that science was going. Albert Einstein, Boris Podolsky, and Nathan Rosen in 1935 wrote a classic paper, Can Quantum Mechanical Description of Physical Reality Be Considered Complete? And basically, this paradox, they point out that what they think they know about particle physics makes no sense because nothing can go faster than the speed of light. They were sure of that. And therefore, they were convinced that Niels Bohr was wrong. Probably one of the best-known contemporary scientists of our day at Caltech is Richard Feynman. He summarized this pretty well, I think. He says, I think it's safe to say that no one understands quantum mechanics or quantum physics. In fact, it is often stated that of all the theories proposed in this century, the silliest is quantum theory. Some say that the only thing that quantum theory has going for it, in fact, is that it is unquestionably correct. The entire field of lasers, microprocessors, computers, hang on the field of quantum physics. It's proven correct. And yet, by recipes. And yet the implications of those recipes are absolutely disturbing. Now, one of the proteges of Einstein is a guy named David Bohm. He's a protege of Einstein's, and he is one of the most respected quantum physicists of our era. He did landmark work at Lawrence Radiation Lab and elsewhere on plasma physics. When he was studying the peculiar behavior of plasma is the fourth state of matter. Most of us know about solid, liquids, and gases. There's a fourth state of matter where the atoms are dissociated. They form a kind of charged gas that has its own peculiar characteristics. He's an expert in plasma physics. As he studied plasma physics, he became increasingly convinced that as a group, the electrons or whatever in the plasma behave in such a way as to imply they know where everybody else is. And it didn't make sense, and it bothered him more and more. And he was the first to perceive the idea that at the subatomic level, location ceases to exist. See, you and I tend to visualize an electron as a little tiny thing, and we assume it's there or wherever. One of the insights that Bohm and Niels Bohr and some of these began to have is that when you get down to that level, the whole concept of location has evaporated. These things don't have specific location. Now, this was being wrestled with over a number of years, but in 1964, a very famous, now famous mathematician, John Stuart Bell, who worked at CERN in Geneva, that's the atomic facility there in Switzerland, he formulated a mathematical approach to trying to address or prove this issue of non-locality. And I won't get into the mathematics of it here. But he formulated this famous equation, or inequality. In 1964, there wasn't the actual technology or resources to actually try to undertake it. It was just a theoretical endeavor. However, in 1982, Alan Aspect, Jean Dalibard, and Gerard Roger at the Institute of Theoretical and Applied Physics and Applied Optics in Paris, they actually, by then, had a means to actually put this to a test. And they did an experiment, which is now, it's been repeated, and it's very, very famous. Basically, they took two photons from heating cesium atoms with lasers, and they did it in such a way that these things would adopt a certain property, and they were traveling in opposite directions, each going down 6.5 meters of pipe, to special analyzers at the end. And the whole point being, the filters that operate here switch in 10 nanoseconds, which is 30 nanoseconds less than it takes these particles, that speed of light, traveling down this. In other words, they could outrun the speed of light by doing it in this particular way. To make a long story short, they demonstrated conclusively that the photons demonstrated non-locality. Each, depending on what they did to one, the other one knew about it immediately. And they were able to prove that. And so this has shattered our notions of reality. The whole idea of the nature of the universe, among people who have been focusing on this and have the background to understand it, it is extremely disturbing. Now, it's interesting, David Bohm has a view that what we are seeing in what we call physical reality, first of all, it's digital. That's one of the reasons it's so profoundly interesting here, because it means that it's all part of it's a result of in this presentation I haven't laid the groundwork of what I mean by digital. If I try to measure temperature with a thermometer, when the thermometer is twice as high, it's twice as hot kind of thing, that's an analog kind of device or presentation. If I have a clock with hands on it that's telling me time, when the hand moves twice as far, it's twice as long, that's an analog presentation. Most of us are familiar with a standard clock face, that's an analog presentation. And you could figure out what time it is even if you didn't have any numbers on it, because you know that it's proportional to the time. A digital presentation is a symbolic presentation. On your car, your odometer is digital. Typically, your speedometer is analog. The further the needle goes to the right, the faster you're driving. But your odometer has digits, 5, 6, 7, 3, 9, whatever, okay? Now, the point of a digital thing is that digital implies a prior agreement. If I had a blackboard here and I wrote M-A-N, spells what? Why? Why does M-A-N spell man? Because we've previously agreed on it. We've agreed on an alphabet of 26 letters. We've agreed that M-A-N, we just agree, means man. It could mean a fire hydrant if we agreed to it. The point is, language implies an agreement between the sender and receiver. Something that's digital is the same way. I'll give you another example. The Old North Church, Paul Revere's ride. He's watching the Old North Church, 1 if by land, 2 if by sea, right? Why? Why, if he sees the 2 lanterns, does he know that the British are coming by sea rather than by land? Because they previously agreed. The British could have had the biggest Cray computers in the world and never been able to break that cipher, would they? Because it's not a cipher, it's a code. It's simply a signal we pre-agree on. Right? Now, it's 2 lanterns. It's actually a 1-bit message. The first lantern goes on in the news, just says that he didn't fall off his horse or off the ladder climbing up there, right? Okay, it tells you nothing. The first bit tells you nothing. You see, it's when the second one goes on, he knows that the British are coming by sea, and of course you all know the story. The point is, that's a digital presentation. Digital communication implies language. If I'm going to communicate to you digitally, or to a computer digitally, I've previously decided that bit, no bit means something. You with me? So if you design a computer, you design the language first, and then you design the engines that process the language. Now, the fact that the universe is digital is staggering, because digital doesn't just happen. It has to be the result of planning. And so it gets hairy. Now, David Bohm suspects that we really have at least two levels of reality. The reality that you and I experience, that we think is real, is the result of digital simulation. And the behavior of the particles underneath that operate like a Fourier transform. They have immediate total interconnectedness. So he suspects that what we're really experiencing in our reality is the result of a super hologram. And he calls this deeper reality the implicate order, and the level of existence that we understand the explicate. You say, well, this guy's just some kind of nut. Well, Roger Penrose of Oxford, Bernard Espegon of Paris, and Brian Josephson of Cambridge, these are three of the most prominent thinkers on the planet Earth, agree with him that this is very reasonable. Something else I want to mention, there are two concepts we use in mathematics, we talk about all the time. One's called infinity, and one's called randomness. Now, infinity, we talk about that a lot, but it's kind of interesting to notice that we can't find it anywhere. Astronomers have concluded that the universe is not infinite, it's finite, it's got a limit. So you don't find infinity in the macrocosm, and that gets back to the whole heat death thing and all the rest of it. You also don't find infinity at the microcosm. You would always think that something we could cut could always be cut smaller and smaller to infinity. And then we discovered, conceptually maybe, but not in reality, because there's a point at which you can't do it. So it turns out that we live in a finite definition of reality in the first place. The other area that's surprising, in mathematics, there's two divisions of mathematics. One's deterministic. That's what most of us have learned. F equals ma or E equals IR or whatever, is that they're equations. And this causes that. And 2 plus 2 equals 4, always. Not a proud 4, right? I mean, whatever it is, the answer is it's deterministic. Most of engineering and physics is deterministic. However, there's a whole other field of mathematics that's typically stochastic variables, random variables. That's where you get in the field of advanced statistics. Well, and they depend heavily on the whole concept of randomness. Turns out, they've now discovered true randomness does not exist. If you deal with random number generating computer, you're talking about a pseudo-random number generator. It generates a stream of numbers that have certain properties that approximate randomness. Turns out, if you get really serious about this and try to find a random number, you can't do it. All you can do is get an approximation. And there's a whole field of mathematics that has emerged out of this study. They call it the theory of chaos. See, there's some things that are very, very ordered, like a snowflake, or like almost anything you think of. But when you take a box of tacks and spill them on the floor, you'd think that's random. But they've discovered it really isn't. Or an explosion of a building. For practical purposes, yeah, I guess it's pretty random. But the point is, there's a whole study of the theory of chaos that says that randomness doesn't exist. And what's interesting, the reason I bring this up, that's exactly what the Bible said all along. That the lot is cast in the lap, but the whole disposing thereof is the Lord. Or the way Einstein summarized the same idea, God does not play dice. Or as the way we would say, if he did, he'd win. But there is nothing, which means, by the way, that none of us are here by accident. All of us are here right now by his divine appointment. Isn't that wild? Yeah. Well, anyway, to put this in perspective, we talked about the fact that speed of light is slowing down. We spoke about the second law of thermodynamics, the bondage of decay. There are some of us that conjecture, it's just a speculation on our part, but we believe that all started in Genesis chapter 3. That prior to the fall of Adam, the speed of light was much faster, the whole atomic behavior was different. You can't prove to me that Adam lived in only 3 dimensions. We presume that because we only know the creation post-curse. In Romans chapter 8, it speaks of the creation as being under the bondage of decay, groaning until for the consummation. It implies that the entropy laws are a result of the curse that resulted from Adam's sin. That curse that's obviously well established in Genesis 3 may be accompanied by the fact that the speed of light started slowing down at that time, which gave rise to all kinds of other issues. In fact, Satterfield has even done some calculations to suggest that it's by the time you get to Genesis 6 that the speed of light is slowing down enough to cause the prism effect to cause rainbows and raindrops. But that's just mathematical conjectures. The point is It also could be that the basic creation fractured to create the 4 dimensions we experience have been withdrawn from the 6 dimensions that are curled. Curled is a mathematical term. It's a vector analysis term. But anyway, the point is that it's very possible that the 4 dimensions of 10 kind of thing, and slowing the speed of light, may be associated with the curse that will be relieved when the second coming, etc. So those are just thoughts to help try to tie that together. This idea of randomness is interesting, but don't assume that everything is predetermined. The fact that randomness, as we would think of it, is an elusive concept physically. We try to deal with that whole issue in our little briefing called the sovereignty of man. The problem is not the sovereignty of God. The problem is the sovereignty of man. Our fate versus free will. And that paradox, that classic paradox, is only a paradox when viewed from within the time domain. Because we in the time domain are free to make a decision. It just happens that God, who's outside that time domain, knows in advance what it'll be. And it's a paradox only because we're viewing it from within the time domain. That's not just a glib summary. It's something, if you're really interested in that, we have a little series called The Sovereignty of Man, which tries to deal with Calvinism, Arminianism, fate versus free, that classic dilemma. The dilemma is relieved if you just go at it with contemporary physics, in effect. It's very possible that this excursion was probably scratching where you weren't itching in terms of our nature of reality, but it's absolutely staggering to understand that our universe itself, our concept of reality, is digital. Now, in this series of studies, we've talked about the Bible and discovered that the Bible is written in code, and those codes are anticipatory. Those codes have come be anticipated events outside the dimensionality of time, and especially in the macro codes that we talked about in the previous sessions. But it's also interesting to discover that the design of these codes in the Bible are also carried over in our lives, and I mean in our DNA. And what we're going to do after a brief stretch break here is go into the second session, which is we're going to talk about the code of life itself and try to tie that into the Scripture.